Hello everybody and welcome to Bite Size Chemistry, and today we are looking at the rates of reactions. Now we're specifically going to look in at the theory of the rates of the reactions. So the experiments will not be included in this video, they will be in another video. And secondly, the graphs and stuff like that, they really can't go in this video as well because the video is going to be too long. They're going to be in a second video too. So this is the rates of reaction theory part 1. Okay, so first off, these are the main questions that we have here that come up all the time in rates of reactions. Definitions in particular, okay, you will see this in some form. So rate of reaction is constantly being asked: activation energy, heterogeneous, homogeneous catalysis, effective collisions. They're coming up the whole time. You're then asked to describe the surface adsorption theory. I find students can overcomplicate this to no end, okay? You can shorten this down quite easily. Factors that affect the rate of reaction come up frequently enough. Energy profile diagrams, you're going to see in this video and part 2 that exothermic and endothermic profile diagrams come up. You should be familiar with them from junior cycle. An experiment here on the oxidation of methanol using platinum wire. We might look at it in this video, but we'll almost certainly look at it in the next video because it's been a while since this has come up. So 2022 is definitely due to appear again. Now it's not a mandatory experiment, so a lot of teachers don't do it. They might show you a video, something along those lines, but you do need to know it. Catalytic converters, the process of it, and conditions necessary for dust explosions. That one doesn't really come up at all, to be honest, but technically it could be asked. So let's get started. 2020, what's the word I'm looking for there, Ryan? Rates of reactions came up in the experiment section. Usually when it comes up in the experiments, it will not come up in the long questions, and vice versa. If it comes up in long questions, it doesn't come up in the experiment section. Okay, so 2020, it came up as an experiment question, so therefore 2019 was the last time it came up as an theory question. You're given a graph here. You're told that A reacts heterogeneously catalyzed by X, forms your two products over here at a certain temperature. Skip all of that, just go straight down to your questions. A, define rate of reactions. I said at the beginning of this video that rates of reactions come up all the time for definitions. It is the change in concentration per unit time. You have to get that. Okay, it's simply learning off. Doesn't matter whether you're doing higher level or order level, you need to know it. The change in concentration per unit time. Now, underneath it, it's asking you to find the average rate of formation of C in the first 500 seconds. So all you're going to do here is you're going to go over to 500 seconds. You're going to go right up to where it hits C. You can see it's 0.002. So your average rate is concentration over time, which will make sure the units are in molarity per second. And this is what you should get. Underneath that, you're asked how does the instantaneous rate at 500 seconds compare? Well, for this one here, you have to calculate the instantaneous rate. I'm not going to do it now. But if you calculate the instantaneous rate at 500 seconds here, you know, your tangent and so forth, you'll find, I'll give you the answer, you'll find that the average rate is greater than the instantaneous rate. Okay, but you'd have to calculate that yourself. Okay. The average rate usually is, if it's a very steep slope at the start, the average rate is usually going to be greater than the instantaneous. C, another definition. Explain the term heterogeneous catalyst and describe the surface adsorption theory. So let's start off with heterogeneous catalysis. Heterogeneous catalysis is where the catalyst and the reactants are in different phases. Now, lots of people think that different states matter, like one's a solid and the other one's a liquid. One's a gas and the other one's a solid, and so forth. Okay, that's kind of the case, but it's very simplistic. In reality is, you could get solids that dissolve in a liquid, and if a solid dissolves in liquid, it is therefore in the same phase. So homo meaning the same. So homogeneous catalysis is an example of that, where the catalyst dissolves in the liquid. If the solid does not dissolve, perfectly fine. You might be familiar with the manganese dioxide experiment, where you put that into some hydrogen peroxide and you prepare some oxygen gas and you got the rate of reaction and so forth. You might notice in the conical flask at the very end of the experiment that you were left with your black powder, and your black powder was manganese oxide. It had not been used up. It had not been dissolved in the liquid. So different phases. You can get some liquids where a catalyst and a reactant, they can dissolve in one another. Okay, so just be careful of that. So heterogeneous catalysis is a catalyst and a reactant are in different phases. Now, describe surface adsorption theory. I told you earlier that students overcomplicate this loads. There is no need. I divided up into 3 steps. Spelling matters here. Okay, it's not often in chemistry that spelling does matter, but this is one of the cases. If you have a spelling wave here or anything along those lines, okay, you're going to be grand, you'll be with it, but if you don't, you do need to know the spelling, particularly of this word here. So reactants are adsorbed, okay, onto the surface, onto the catalyst surface. So step 1, the reactants are adsorbed onto the catalytic surface. The reaction takes place onto the surface, and then the products desorb from the surface. Now, you can add more to that. You can talk about temporary bonds and so forth. You can talk about active sites. But in any marking scheme that has come up so far, this is literally all you need. Reactants are adsorbed into the catalytic surface. Be careful with the word adsorbed. If you use AB, for instance, you will lose marks. Next, explain why pellets of X would be less effective as a catalyst than the same mass of powdered X. So why would the pellets of a catalyst be less effective than a powdered X, or the catalyst? Well, that's got to do with size. And when it comes down to size, everything's got to do with surface area. Now, for surface area, you want it to be as large as possible. The larger the surface area is, the faster the rate of reaction. So if it's a powder, it will have a large surface area, whereas if it's pellets, it won't. Think of it like cooking potatoes at home. You know, if you cut the potatoes up and boil them, they're going to cook a lot faster if you had the potatoes full when you were boiling them. Okay, by cutting up the potatoes, you are increasing the surface area. So the smaller the particles are, the larger the surface area. So just to show you the writing for it, pellets are bigger size than the powder, so therefore pellets would have a smaller surface area. Okay, so meaning they'd be less effective. Now, D. Without X, this reaction has a large activation energy. Explain the underlying term. So, one full question there, and there's 3 definitions come up. Activation energy. This is the minimum energy required for colliding particles to form an effective collision. Now, you must use the word minimum energy. That has to be in the definition. So, activation energy is the minimum energy required for colliding particles to form an effective collision. State and explain 2 ways of increasing the rate of reaction other than that of a catalyst. Well, there's a couple of different ways. I'm going to put in 3 ways, the most common ways. You can increase the concentration of the reactants. The more reactants that are present, okay, the more likely a collision is going to take place. You could also increase the temperature. The higher the temperature, the more energy involved in the kinetics of the reactants, the more likely a successful collision will take place. And finally, you could decrease the particle size. By decreasing the particle size, you're increasing the surface area. So any of those 3 would have been fine. Now be careful here. Students often make the mistake there. They say temperature, they write down concentration, or they might write down particle size. And they get no marks. One word answers simply is not good enough. Okay, you must say the word increased concentration, increased temperature, decreased the particle size to get full marks. So I stated and explained 2 ways of increasing the rate of reaction. Is this an equilibrium reaction? Explain your reasoning. So if you have not done chemical equilibrium just yet, this one won't make too much sense, but if you have, you can pay attention. So anyone who studies equilibrium knows that the reactants are forming the products, products are forming the reactants. It's a dynamic situation happening, a dynamic reaction taking place. And if we look at A, which was our reactant to start off with. That was catalyzed by X. A over here is this guy over here. And we can see as A starts off with a certain concentration, and over the 3000 seconds it decreases. And in fact, by the time it gets to the end of 3000 seconds, it's a 0. So therefore it has been all used up. Well, because it's all been used up, it cannot be an equilibrium reaction. The reactant will never disappear if it was an equilibrium reaction. So I wrote down no, Y, and then I just say A is all gone at the end of the reaction. And that's it. Okay, so that was the bulk of the definitions type of questions that are going to be asked, and a few others. So starting off, what is define rate of reaction, what is meant by activation energy. So 2018, the exact same definitions are coming up again and again. Change in concentration per unit time is the rate, and obviously the activation energy here is the minimum energy required for colliding particles to form an effective collision. Graph paper there, you have to draw out your graphs. I'm not going to do that now with you guys. You have to find the instantaneous rate. Okay, I have a picture of it here. You'll have to pay attention to that one in your own time, or the next video that I'm going to be doing. So just to bear that in mind for now. Now, D, you didn't need a graph for this. Suggests a reason why NO is not formed in every collision between the NO2 particles. Okay, so if the product is not formed in every collision, it means there is not enough activation energy. It hasn't enough energy to reach the activation energy, and therefore a successful collision cannot take place. So I wrote down reactants didn't have enough activation energy. That was all. How could I increase the frequency of collisions? A couple of different ways there, guys. I suppose increasing temperature is the most obvious one. Or you can increase the concentration of the reactants. Finally, you could also, if it's allows for it, to decrease or increase the pressure, so therefore you're decreasing the volume. That's the same point. That's not always possible though, because of different things, like, it might be the container you might be using might be a solid container, cannot be moved or whatever. So really, if you're answering this, I would go with temperature and concentration. Okay, a labeled reaction profile diagram for this reaction. So there are two types of reaction profile diagrams, exothermic, endothermic. So you go over here, you look at your delta H over here, and you can see it's a positive sign in terms of kilojoules there. So therefore, it must be endothermic, your reaction energy profile diagram. Now, you have to learn this diagram off. Same for the exo. It comes up too often, and when it does come up, it could be 6 to 9 marks. Okay, make sure you know those axis titles. Make sure you know the reactants, the products, what the EA stands for, the activation energy, the your delta H and so forth. Okay, now in hindsight, that graph here, or that energy profile diagram, could have been better. So spend a little bit of time at it. Okay, 2015. What is a catalyst? Okay, it's a substance. You should know this from junior cycle, but it is a substance that alters the rate of reaction without being used up itself. Explain how the type of bonding in the reactants influences the rate of a chemical reaction. Now, whenever it comes to type of bonding, they're looking for ionic or covalent. Okay, you don't need to worry about non-polar or polar covalent or anything along those lines. Just ionic and covalent. Now, you learn it off. If it's ionic, the reaction is going to be very, very fast. In fact, it'll always be instantaneous, because no bonds need to be broken, because they're ions. An ionic bonding is oppositely charged ions attracted to one another. Whereas if it's covalent bonding, the reaction takes a little bit more time, because bonds need to be broken first before they can be reformed to form your product. So that's come up once or twice, and it's definitely one worth knowing. Difference between ionic and covalent in respect to rates of reaction. Now, the last part of it was, how could you reduce the rate of reaction that takes place in the solution? Now, you can see I have the word reduce highlighted. A lot of students didn't get the marks for this. They assumed when they read it, how could you speed up the rate of reaction? Because the majority of the time it will be speeding up the rate of reaction. Now we're slowing it down. Well, it's very similar. we lower the temperature or we lower the concentration of the reactants. Okay, either of those two will get you full marks. That's how you slow it down. And again, don't forget to make sure you read the entire question, because obviously this is two parts of B here and it's not very clear, so you just make sure you go through all of it. Now, this is the oxidation of methanol using a platinum wire as a catalyst. So it's come up a few times. 2015 was the last time it came up, so it's definitely overdue. And anyone sitting the 2021 paper, possibly 2022, depending how the leaving cert goes, I would be surprised to see this come up. So state one observation made during this experiment, identify two major products of the oxidation. Very common questions. Now, it's really ideal for you to have done 2 chapters prior to this. The first chapter being oxidation reduction, just to understand what oxidation actually is. The second chapter to be the types of reactions in organic chemistry. So you'd be familiar with methanol, and when it's oxidized, forming methanal. So no harm to know those as well. So an observation during it, and 2 major products. Well, first off, there are actually several observations one could make. The platinum wire glows, you get a popping sound, you get a smell of methanal, the flask gets hot. Spelling matters here for methanal. Be careful, methanal, very similar, just to be careful with that. So there's 4 observations that you can make here. And the 2 products, well, there are 3 products in total, so I might as well give you all 3 of them. Hydrogen gas, which is why there's a popping sound. Hydrogen gas. Methanal, obviously, because there's the smell of methanal, and you get water there as well. So there'll be a bit more of a liquid. There'll be methanal and water in the liquid. The flask gets hot, meaning it's exothermic. What term is usually used to describe the attachment of a liquid or gaseous molecules to a solid surface? Adsorption. ADSORPTION. The next question perhaps is probably the trickiest out of all the questions that have been asked for this experiment throughout the years. Explain how this type of interaction between methanol and the platinum catalyst affects the rate of reaction or the rate of oxidation. So what you had to say for that, and I wasn't sure at the time myself, being honest with you, but you had to say there that the methanol adsorbs onto the catalyst. There is now a higher concentration, okay, and then your methanol bonds become weakened to form, because it's covalent bonds, to form what's the word I'm looking for? Methanal eventually by oxidation. So you need to say higher concentration and the methanol bonds are weakened. Probably an unfair question, really, the way it was phrased. Yeah. Okay, the next one, the final one here of part D, everybody. Explain how a catalyst poison like sulfur interferes with the catalyst. So sulfur compounds and lead compounds, both of them are catalytic poisons. So how does it do it? Well, what happens there is any catalyst poison, doesn't matter whether it's sulfur or lead, okay, they all do the same thing. They form permanent bonds with the active site on the surface of the catalyst. Okay, so by doing so, they're blocking the surface. Okay, so the catalyst poisons block the surface active sites by permanently bonding, which is obviously a problem. Underneath that, explain the term activation energy and draw an exothermic reaction, which you can see over here. Exothermic, your definition for activation energy. We've seen that come up time and time again. Okay, the last one for this video, 2014. I'm not really sure what question this is. I think it's like question 7, but I might be wrong there. You'll find it. So you're given a catalytic converter. You're asked to talk about that. So name 2 metals used as catalysts in catalytic converters. Well, there's 3 you should know: platinum, palladium, and rhodium. Okay, you should know all 3. You're only asked for 2, however. What type of catalysis occurs here? It is heterogeneous. Okay, because you have gaseous molecules attaching, adsorbing onto the solid catalyst. So 2 different phases going on there. Give one way in which a catalyst increases the rate of reaction. Well, the only way that you should know for how catalysts work is that they lower the activation energy. Lowering the activation energy means that the molecules, when they collide, are more likely to form a product. And finally, name a substance that could poison the catalysts. Well, we said it 2 minutes ago. Sulfur compounds or lead compounds, both of which will poison catalytic converters. And that's it. Now, that's it for part 1 of rates of reaction theory. You'll see that throughout part 1 we answered most of the main questions here. And part 2, very repetitive, similar setup again. Okay everybody, I hope you took something from that, and best of luck with your studies.